Start our lecture. I hope you have all seen the outline of the course and you've started looking for the textbooks as well. We are talking to the library if they can get a large number of textbooks into the library so that you can purchase. So we'll let you know what our outcome is of the discussion with the librarian. So today we're going to extend our discussion from the previous lecture, that is on Friday, and we're going to talk about cavity radiation in 3 dimensions. If you remember, we discussed that there was a large number of experiments that took place between the 18th and the 19th century which revealed the cavity radiation curves of the following form. So this is the spectral irradiance on the ordinate axis and the frequency on the abscissa on the x-axis. As the frequency increases, the radiance increases and then it drops. So that when the frequency goes to higher values, the radiance drops. So these are experimental curves and a large number of scientists were able to find experimental data points for different frequencies and different temperatures, and they resulted in similar curves. We also know that we can plot the same curve, and instead of plotting the spectral radiance, we can plot another quantity which is the energy density. So if you have a black body, it is basically a cavity. These are the walls of the cavity, and radiation is trapped inside the cavity. So this is cavity radiation, and the cavity radiation is at a temperature T. If we take a small volume of the cavity, find the total energy inside the cavity for unit frequency, we call it the energy density. So this energy density has units of joules per cubic meter per hertz. So take a small volume inside the cavity, find the total energy inside this volume, and the energy comes from the electromagnetic waves, the standing wave of the cavity radiation that has been set up, and divided by the frequency interval. So you get exactly similar curves. So how did quantum theory come into existence? Quantum theory came into existence in an effort to explain these curves mathematically. So the experiments had preceded the theory, and there were a large number of theorists who were clamoring, who were working very hard to come up with a mathematical expression for rho versus the frequency. And that is what we are going to do today. On Friday, we looked at the problem in 1 dimension, so that you can motivate the problem. Looking at the problem in 3 dimensions is somewhat more complicated. That is why we looked at the problem in 1 dimension on Friday. Now we will use the same concepts and extrapolate to 3 dimensions. We'll talk about how the radiation is trapped inside the cavity in 3 dimensions. Now in 3 dimensions, the same general rules apply. That is, the electric field at the walls must be 0. Therefore, a 3-dimensional standing wave is set up. Now when a 3-dimensional standing wave is set up, you can write the electric field associated with the 3-dimensional wave as following. The electric field is E, certain amplitude E0, and the sinusoidal term sine n pi x over L, where L Suppose this cavity is three-dimensional and it's cubical. It's a cubical cavity. That is, the length along each dimension is L. So we have sine n pi x over L. This term ensures that at x equals 0 and x equals L, the standing wave disappears, and n tells you what mode it is, whether it's the first mode or the second mode or the third mode. This is what we wrote for a one-dimensional cavity. Now for 3 dimensions, we will have another term corresponding to the y dimension. So we will have a sine n pi y over L. But this n must come with a subscript x. This comes with a subscript y. And we have a third term, sine nz pi z over L. And we have a time dependent term as well, sine 2 pi ft. So this is the most general form for a standing wave of an electromagnetic field in 3 dimensions, and it ensures that at the walls of the cavity, the electric field disappears. Now I cannot draw the 3-dimensional wave. In 1 dimensions I could easily draw the standing wave patterns in fundamental mode, the first harmonic, the second harmonic, but being a human being, I cannot draw the 3-dimensional wave on a 2-dimensional blackboard. I can use computer simulations so that we can graphically visualize this wave, but I can't draw it in the classroom. However, what is important to realize is that each mode is characterized by 3 numbers, nx, ny and nz. In 1 dimension we only had one n. Now we have 3 kinds of n's, nx, ny and nz, and they define the mode, and each one of them is a positive integer. So nx, ny and nz, all the trio of these numbers, ये तीनों नंबर डिफाइन करते हैं मोड को. तो हमारे पास कौन कौन से मोड्स हो सकते हैं? We can have 1, 1, 1. This is the fundamental mode in 3 dimensions. When nx equals 1, ny equals 1 and z equals 1. This is the fundamental mode. ठीक है? अगर इनमें से कोई भी 0 हो, the wave will disappear because the electric field will disappear. So the fundamental mode is when nx is 1, ny is 1 and nz is 1. ठीक है? ये अगर 2 dimensions में आप देखें, एक ड्रम लें, ठीक है? Let's take a square drum, ठीक है, जिसके ऊपर मेम्ब्रेन है. उसमें फर्स्ट मोड क्या होगा? फर्स्ट मोड ये होगा, this is a 2-dimensional drum. The first mode is, if I try to draw the first mode, it will look something like this. That is, there will be nodes at the ends, at the corners, and it will be stretched at the top. This is what the first mode will look like in 2 dimensions. Likewise, I can draw the first mode in 3 dimensions. I can attempt to draw the first mode in 3 dimensions, but I will not undertake this task here. Anyways, the first mode is when nx, ny and nz are all 3 of them are equal to 1. What is the next higher mode? Is when one of these numbers equals 2. So I can have 2, 1, 1, I can have 1, 2, 1, I can have 1, 1, 2. This means that for this particular configuration, there will be one antinode along the x-axis, there will be one antinode along the y-axis, one antinode along the z-axis in the middle. And likewise, I can generate all the modes. ठीक है? अब हम ये देखते हैं कि we want to find the number of modes with frequency less than or equal to 1. We want to find the density of modes, and we want then to multiply it with the energy of each mode. Okay, if we talk about 1 dimensions, देखो वन डायमेंशन की मैं दोबारा बात कर देता हूँ ताकि आपको क्लियर हो जाए. अगर एक डायमेंशन की बात करें, द इलेक्ट्रिक फील्ड इज E नॉट साइन n pi x over L. This is the electric field in one dimension. Now when n equals 1, there is only one kind of n here. There is only an nx, one kind of n. When n equals 1, your standing wave pattern looks like this. ठीक है? There are nodes here and one anti-node in the center. ठीक है? ये standing wave pattern है ना fundamental का. If n equals 2, your standing wave pattern looks like this. There are two antinodes. ठीक है? When n equals 3, there are three antinodes. 1, 2, 3. इसी का standing waves बनेंगी ना. अब इस पूरी आर्ग्यूमेंट को 3 डायमेंशंस में हम एक्सटेंड कर सकते हैं. एक 3 डायमेंशनल वेव बन रही है जिसका फंडामेंटल मोड में सिर्फ एक एंटी नोड मिडिल में एग्जिस्ट करता है. यहाँ पे एक एंटी नोड होगा बिल्कुल मिडिल में 2 डायमेंशंस में. 3 डायमेंशन में भी बिल्कुल इसी तरह एक एंटी नोड होगा इन द मिडिल. और हायर मोड्स में द नंबर ऑफ एंटी मोड्स गोज ऑन इंक्रीजिंग. सो विजुअलाइज अ 3 डायमेंशनल वेव ऑफ अ स्टैंडिंग वेव in a cavity in which as you increase the number of modes, increase the order of the mode, there will be more and more antinodes or more ripples of the standing wave inside the 3 dimensions. Alright, you can say that. But in 3 dimensions it gets complicated. Alright. So how do we count the number of modes in a particular frequency interval? Because what we really want to do is we want to write a formula for the energy density, the function of